Hi, I'm Collin B. Whittaker, a sixth-year PhD candidate with the University of Michigan's Plasma Dynamics and Electric Propulsion Laboratory, and I'm back to talk about using electrosprays as miniature rockets in space. If you've seen my previous videos, you may already be familiar with what an electrospray is, but for those who aren't, I like to think of an electrospray as a liquid lightning rod. A lightning rod works by using a sharp point to amplify electric fields, creating a place where an electrical discharge likes to form. In the same way, we make electrosprays as small needles. Now on Earth, the voltage driving the discharge comes from storm clouds, and the lightning arcs through the air itself. But in space, there is no air, and certainly no storm clouds, to do this. Instead, we use a power supply to provide the voltage, and we feed in an electrically conductive fluid to form the discharge, which manifests as a spray of electrically charged particles, electrospray. The force of this beam being ejected from the needle produces a reaction force in the opposite direction, pushing our spacecraft. The key downside with electrosprays is that they're really small, often a few hundred micrometers tall, about the size of a single pixel on your screen. Correspondingly, one needle, or emitter, doesn't provide much thrust, less than 1 micronewton, say, and often much less than that. For perspective, a person in the US weighs about 750 newtons. So if you wanted to try to lift yourself off the ground, you'd need over 750 million emitters. And even then, it wouldn't really work, because the electrospray themselves would be heavier than that. That's not a problem in space, though, and so we can take advantage of the fact that electrosprays are very fuel efficient, like other forms of electric propulsion. That is, they can take you far away using very little propellant, even if it takes them a while to get there. Needing to aggregate many emitters together represents a real challenge to making larger electrospray systems that can push satellites around in space. In particular, when you manufacture a bunch of emitters, it's impossible to guarantee they all come out the same. This is problematic because it means some emitters could be running hotter than others, which can cause them to fail early and potentially disable the entire thruster. A few bad apples spoil the bunch. This is where my research comes in. Over my PhD at PEPL, I've worked with a number of techniques we can use to quantify uncertainty in emitter performance, from characterizing variations in geometry using surface profilometry, to calibrating models for individual emitters, and then combining these two to make predictions of array performance with confidence. This analysis gives us a powerful framework that we can use to help design systems that are more robust to these sources of uncertainty. But it's always important to validate our predictions against real experiments. To do that, I designed and built the Michigan Electrospray Array Thruster Series 1 version 2, or MEET 1.2 for short. This system is 90 millimeters on each side and contains over 6,000 individual emitters, which is enough oomph to really put our design tools to the test. In partnership with NASA's Jet Propulsion Laboratory, we were able to test the MEET 1.2 in a facility designed to simulate the vacuum of space. A beam dump helps prevent the ion beam from being reflected back at the thruster, and probes help us measure what's going on in the facility, which we can represent more schematically like this. We gradually increase the voltage supplied to the thruster to see how much current it sources, and this is what we saw. The thruster first turned on at about 350 volts with barely any spray, only about 1 microwatt of power. But at 2000 volts, the thruster was sourcing nearly 11.2 watts. While this maximum power is only equivalent to a single LED light bulb, it's about 10 times more powerful than most similar systems. We also performed some other experiments where we put the thruster on a scale to measure exactly how much thrust it was producing and how much fuel it was using. We observed that the thrust increased with power as you would expect, peaking at about 174 micronewtons at 1.7 watts. We wanted to test at even higher power, but this smaller vacuum facility couldn't keep up. In addition to thrust, we measured specific impulse, the fuel efficiency of the system. We observed that above half a watt of power or so, our specific impulse dropped. This wasn't something we expected to see, and it highlights the importance of performing validation experiments. They let us recalibrate our models to capture what we observe and make more confident predictions in the future, which will be a continued aspect of my research here at PEPL. Well, that's all the time I have, and thanks for listening. Check out some of the other research going on at PEPL on our channel. Goodbye.